This is Mina Lesson. I want to present this presentation for you. The title is so long and it's said in a brief. We want to understand the effect of a system, a wind catcher system which is integrated into two main air ducts that are buried under the ground. This affects the mean indoor temperature and indoor microclimate. Therefore, in this presentation, first we define the system for you in a case study model, and secondly, we discuss why we use this system for studying. Then, research methodology is outlined, and finally, the results and findings are discussed. Wind catchers are passive cooling systems have been used for centuries in hot and humid climates of Iran. They located on the roof of the buildings and captures the outdoor wind and directs it into interior. Wind catcher was oriented to the prevailing winds to cool the startup space. In Kashan, which is located in a hot and arid climate with high temperatures in summer, wind catchers are integrated to air stacks or Nikesh to cool the startup space. Wind catcher of Tabatabai House was selected as a case study in this article. Wind catcher had a height of 17 meters and it is directly connected to the startup space and uh, two main air ducts. The purpose of this study is to understand the hydrodynamic behavior of this system and how it changes indoor microclimate. According to literature review, it was found that most studies have been conducted on wind catcher elements. For example, roof shape, total shape, plan design, and even wind catcher height. And also, these studies have focused more on ventilation performance rather than thermal performance. This study is different in some way because in this study, the wind catcher is integrated to two main earth ducts which are connected to directly to surface space and cools it and have effect on the interior microclimate of the house. The experimental and numerical methods used to evaluate the hydrodynamic behavior of wind catcher integrated into air ducts. Field study was used for experimental method and CFD as a numerical method. The on-site recorded temperature and wind data were used as a boundary condition in CFD software, or the experimental recorded data was used as a boundary condition in CFD simulation or in numerical method. The results of the CFD simulation were compared with the empirical mean on-site temperature, and 8.2% found for discrepancies between the numerical and experimental data, and it was logical. To monitor the thermal behavior of the wind catcher in hot and severe days in month of July, 4 temperature sensors were installed at different locations in a wind catcher system. T1 was located to measure the ambient air temperature and has the same height as the air velocity sensor height. T2 is located for measuring the air temperature at the lower part of the wind catcher where the wind catcher is directly connected to the startup space. And T3 is a temperature data recorded in front of the B2 earth duct, which is directly connected to the Sardaba space. T4 is located for measuring the internal temperature of the Sardaba space. The data gathered from these sensors and was averaged, and it was calculated 42 centigrades, and this was used for the inlet boundary condition for CFD simulation. The mean temperature of 42 centigrade was also monitored in 25th of July at 3 p.m. We use this as a target day to compare it with the results from the CFD simulation. Besides temperature sensor, we also put velocity sensor at the northeastern direction. We used northeastern direction to put velocity sensors based on the data from meteorological station. Velocity sensors was mounted at 4 meters above the street level. We need this data to model ABA flow for inlets of the boundary condition for CFD simulation. We can see the wind velocity profile, and it is important to have a correct wind velocity profile because it helps you to have a correct CFD simulation. In order to model the ABA flow, we used both the meteorological station data and also the data which was gathered from the velocity sensor. Based on the meteorological station data, the prevailing wind has the average velocity of 3 meters per second at a height of 10 meters above the ground. And for modeling the urban space profile, Escher equation 2009 was used. Based on the Escher equation, we can calculate wind velocity in different urban contexts and also different heights. Kashan falls under the class 7 in the definition by Ashray. Therefore, at the height of 4 meters above the ground in urban context of Kashan, the wind velocity calculated 1 meter per second at the height of 4 meters, which velocity sensor was located also. In addition, the air velocity at the target day of 25th of July was approximately 1 meter per second. Based on the Ashray equation, which calculated wind velocity at different heights, the ABA flow was modeled. Boundary condition is an important parameter to have a correct model and have a correct CFD simulation. Choosing the right parameters are important to have a correct model. Modeling ABA flow is really important to have correct results, and it was discussed in the previous slide. And pressure outlet is put to 0, air temperature is 42 centigrade, soil temperature is 19 centigrades in this study, and no slip was used as a wall conditions, and roughness height is equal as you see in this slide, and roughness constant is equal to 0.5 in this study. The system has a clear effect on the entering ambient air temperature. It reduces the air temperature of 42 centigrades to 24 centigrades while passing through the air ducts. We have the air temperature of 31 centigrades at the opening, which directly connected the wind catcher to the Sardab space. And also, the temperature at the center of the Sardab was calculated 32 centigrades. We can see that the system has a clear effect on the entering ambient air temperature. This study was conducted to analyze the hydrodynamic behavior of the case wind catcher system and the effects of it on mean temperature of the startup. In this system, we have one wind catcher, a startup space, and a courtyard. This is a system that can work correctly and can help to reduce indoor air temperature. In this system, the hot ambient air comes to the wind catcher and flows down through the wind catcher. And after passing the wind catcher and the air ducts, it cools down and enters the startup space. Now the startup space is cooled with this system. But the startup space is connected to the courtyard, and the courtyard has a higher temperature. The, uh, because of the pressure difference between the startup space and the courtyard, the higher pressure air in the startup space moves toward the courtyard. This circulation causes the hotter air in the courtyard flows down to the startup space, and this circulation occurs. This circulation causes the air temperature of the startup to be risen because the hot air of the courtyard is coming toward the startup and increases its temperature to 32 centigrades. Knowing these systems and other systems can help us to create more green buildings, and knowing these systems can help us to create more efficient and more creative designs in future.